Okay, so basically I've got the simulations in here now, so that's another one we may look at in a moment, but let's just look at this one. So if we go into here, play again. Okay, so we've got two circuits. One of them they're both connected to a battery. One of them we've got light bulbs connected in parallel, or one of them we've got light bulbs connected in series. We can see straight away that for some reason they seem to be going a lot faster in the parallel one than they are in the series one. But the batteries should be the same. So if you take a voltmeter, you can measure the battery, and that one's 9 volts. Let's check this one out as well, and that one's also 9 volts. You look at the individual light bulbs, and that one's 4.5. If I take this one and put that there, and move that one up there, and that one's 4.5. Now, if we do the ones in parallel, they're 9 volts, just the same as the battery. So the ones in the ones that are in series, when you added up the voltage across each light bulb, it ended up being the same as the battery, whereas the ones in parallel had the same voltage that the battery had. So, so do you know what voltage is? I guess. Well, actually, you're on the right track. Actually, it is to do with energy. So a lot of people have a rough idea of what current is, but get very confused at what voltage is. It's the energy. More specifically, it's the energy per charge. Okay, so I'll just write that down. Just summarize here. So the battery was in both cases 9 volts. And but for some reason, when you looked at a voltmeter across each of the light bulb, then it was 9 volts, and the voltage across each of those light bulbs they added up to 9 volts. Now, you said it was something to do with energy, and you're right. Basically, it's like this: energy. So voltage is equal to the energy per charge. So if you have like a big pile of electrons which represent a certain amount of charge, so all electrons have charge, and we want to see how much does this pile of electrons have, how much energy does this pile of electrons have, then we're talking about voltage then. So it's the energy per charge. Very similar to just energy, but it's not just the energy, it's the energy per charge. Okay. So why is it then that the energy? So what is this voltmeter measuring here? Because why are we measuring it in two different places? The reason is because the voltmeter actually measures the change in energy per charge. So when I say the energy per charge, it'd be more accurate to say it's the change in energy per charge. Okay, so change in. Okay, so if you think about it, the electrons that have come out of this battery, for one thing, actually, let's just have a look at. We said that they're going faster in the parallel circuit, but if I move this down here, maybe it's not. I'm gonna have to. Well, it's difficult to do it because. But if I just twist it around a little bit, you can see the electrons here and the electrons there. They're actually not going. They're going around about the same speed. Oh, now I've got it all tangled up. I wonder if I can. They're all tangled up now. I don't know how they all got how that happened. What I was trying to demonstrate is that the electrons are not necessarily going faster in the parallel circuit, but they're going about the same. They're going about the same speed in some areas. So let's close this down, and we'll do it as a circuit diagram. And we can start making some notes. So circuit diagram of what we just saw there was we had, in fact, let's zoom in here. So we have a battery. Well, this is a cell. So a battery would be more than one cell, which can be drawn like that. And we have a light bulb there. And really, when you're drawing these in the exam, you should do a better job than me and not leave any gaps like that. They should all be joined up. because otherwise you're basically saying that the circuit's broken, and it's not. If the circuit was broken, we wouldn't have wouldn't work. The light bulbs wouldn't light up. So, and then we had another battery with, now we had them in series. And what we saw was that the voltage here was 9 volts and there was 9 volts. When we put the voltmeter across this light bulb, it was 9 volts, and across this one, it was 9 volts. And when we put it across this one, it was only 4.5 volts, and across this one, it was 4.5 volts. We said that the voltage is equal to the energy per charge. So Q is the symbol for charge, E is the symbol for energy, and you can actually calculate it. So energy divided by charge, or energy per charge. Now, if you think about it, the electrons would actually move this direction. If we're looking at the battery like that, it would move that direction. And then when they get here, they could go up here, or they could go down here. They could go either option, and the reason why that's important is because any one electron, once they leave the battery, will only go through one light bulb, whereas in this case, every electron goes through both light bulbs. And so the energy that the electrons have must be shared across these light bulbs, whereas in this case, they can use all of their energy up on whatever light bulb they choose to go through. Well, not choose, but whichever one they end up going through. So basically, voltage in parallel will be the same as the voltage across the light bulb. All voltages will be the same in parallel, whereas in series they would add up to the battery there. And I said that the voltmeter. So when we set a voltmeter, like let's do one here, that is measuring the change in energy per charge. Okay, so voltmeter measures the change in energy per charge. So that's why you have to have a voltmeter measuring before and after. And so it needs to be in parallel because it's measuring the energy per charge before compared with after. Now, we also call this potential difference, or PD. And the potential difference is the loss in energy per charge between 2 points. So we measure potential difference across here. Often what you call this thing here is EMF. And that's basically, this is why voltage can be so confusing, because there seems to be so many words for seemingly similar or slightly different types of voltage. Really, you can just get away with thinking they're all just voltage. At GCSE, you wouldn't make any mistakes there. But if you do want to know the slight difference, potential difference is what you measure across a component, and so we're losing energy per charge as you go through the component, the light bulb, buzzer, or whatever it might be, and the EMF is the amount of energy gained per charge as the electrons go through a battery. So in other words, so just to summarize, then the voltage is the same in parallel, and they add up to the original in series. So voltage is equal in parallel, and in series we say V total, or VT, is equal to V1 plus V2.